Well, for our final speaker today, we have Karen Smith from the University of Michigan, and she's going to talk about line of the extremal surfaces. Go ahead. Thank you.
Thank you, Luis. So before we get started, I think we should all thank Luis and Jack for organizing this very nice conference. It's not easy with the online format. Speakers, you're never sure they're going to show up or fill out their forms or pay for their registration. And so if we all could clap somehow. I can't do it when I'm sharing screen, apparently. I don't know how to do it. But thank you. And thank you for inviting me in particular. Okay, so also I wanted to apologize in advance because my iPad died. I just mentioned this to Luis, you may have heard me, in between testing it today around noon and now. So I quickly filled out some of these slides and I'm going to try to write on them with my mouse. I got pretty good at that when I was teaching online. So hopefully it'll be all right, but it'll slow me down a little. It's probably not a bad thing, I guess. Okay, so I want to talk about lines on extremal surfaces. I'm going to define all of this. And I may not mention every list of collaborators on every theorem because there's a lot of them. So the main theorems I wanted to bring up today, which are new and not yet written up, I mean, they're in the process of getting written up, are joint work with Anna Brozowski, Janet Page, and Tim Ryan. Very classical geometric work we're doing that I want to just tell you at least the main theorems about. But it's all built on work that I did with this group of authors. And actually, Eloisa was involved a little bit in that too. I think she might be here. So thanks to her contributions in the very early discussions on these things. If you would like a source for this, these two papers are both on the archive with those authors. And the first one is to appear in Transaction. It may have just appeared electronically in Transactions. Okay, so very classical geometric. Let's get started. Is this advancing? Can you see the slides? Okay. So let's just warm up by remembering classical algebraic geometry about cubic surfaces. So by cubic surface, I just mean a surface in P3, three-dimensional space, projective space, over an algebraically closed field, defined by one homogeneous polynomial of degree 3. And for the purpose of keeping the talk simple and going into the classical world, we're always going to assume all our surfaces are smooth. That just means that this ideal generated by the partial derivatives of that homogeneous form generates an M primary ideal. So that's cutting out a smooth hypersurface in P3. So probably everybody knows this classical theorem about cubic surfaces. Smooth cubic surface. Always, so I'll try to write this. A smooth cubic surface contains exactly 27 lines. So this is a real famous old theorem. Everybody probably knows it. It's in Hartshorne's book. And here I got two pictures that I borrowed from Oliver Labs from the internet that show some cubic surfaces and some of the lines on them. Of course, I'm only drawing these are only the real points. The lines may not be defined over R in general, but we're interested in algebraically closed fields. Throughout the talk, I'm always going to assume the field's algebraically closed. So there'll always be exactly 27 lines on any smooth cubic surface. And notice they can intersect, they do intersect. That's what we're going to be interested in, is these configurations of lines on what we're going to call extremal surfaces, which will be somewhat like cubic surfaces. All right, so let's talk about hyperplane sections of cubic surfaces. If I take a hyperplane, by which I mean just the zero set of one linear form, right? That will be a copy of P2. I can think of that as a copy of P2. I intersect X with that, and I will, of course, have a cubic curve, right? I can eliminate one of the variables. I'll have something inside of P2 defined by a homogeneous form of degree 3 in 3 variables. So it'll be a cubic curve. Most of the time, if I take a general hyperplane section, Bertini's theorem says it'll be a smooth cubic curve most of the time. General hyperplane section, it'll be smooth. However, if the hyperplane I take, I'm saying hyperplane, but it's a plane, right? It's a plane in P3. I take a plane section, I intersect it with my cubic surface. If that happens to be tangent, if the plane happens to be tangent to the surface, then I'll get a singular cubic. There'll be a singularity at the point of tangency. And most of the time, it will look something like a cusp. It'll be some kind of a singular cubic. It'll be an irreducible curve with one singular point. However, it could happen that we get, instead of an irreducible singular cubic, we might get a cubic that contains a line. So we might have a line on the surface, and one of the hyperplanes containing it intersects, or actually all the hyperplanes containing it intersect in the union of that line and something else. So that something else is going to be some conic, right? In this case, and if I take my cubic surface and I take take a plane containing a line on it, generally what I'm going to see when I intersect them is that line and a conic. Now that conic can degenerate in some very special cases, right? One very special kind of a conic is a union of 2 lines. And so the union of we could have a plane section like this. This is called a tritangent plane section, or a triangle. I'm going to call it a triangle because we see it makes a triangle. It's like 3 lines making a triangle. And these 3 points will be points of tangency of that plane with the cubic. I tried to have a picture here of that kind of a thing. All right, so, but there's an extremely special thing that can happen where it could happen that the conic is degenerate and the line passes through the intersection point. Now this can happen on cubic surfaces, and it does happen. This is called an Eckart point in classical algebraic geometry on a cubic surface. And let me go back a previous page because I think there are a few Eckart points on here. Yeah, down on this second one where you see the yellow line. Let me try to circle this here. That blue dot is an Eckart point. There's 3 lines on the cubic surface coming together in one point. Now on a general cubic surface, we don't expect any Eckart points. This only happens on special cubic surfaces. But it can happen, and it does happen, and people have studied them. There's at most, in classically, over the complex numbers, there's at most 18 Eckart points on a cubic surface, and there's a lot that's known about them. But now here's a question you could ask. Are there any cubic surfaces at all, any cubic surfaces, where there's no triangles? Whenever I have one of these tritangent planes, the lines always meet in a point. The lines are always concurrent. Can this happen? So if you ask a classical algebraic geometer, somebody who thinks over the complex numbers, they'll say no, because it doesn't happen over the complex numbers. It does, however, happen in very, very special cases. And this is one of the theorems. This is a theorem the paper that just came out in the transactions for this can happen. So the answer is yes, but only in a very special case. So only when the cone, let's look at the cubic surface as homogeneous coordinate ring. So here's this is the homogeneous coordinate ring, right? The homogeneous coordinate ring. It can only happen when this is not F pure, if anyone knows what that means, or not F split is an equivalent thing. And this can happen equivalently. It can only happen only when the characteristic is 2 and this homogeneous form, this 3 form here is of this form. X squared, well, let me put it this way. It is F, this cubic form is in the ideal generated by, this is it called a Frobenius power of the ideal. We're in characteristic 2. Oops, that's a 2. Okay, so these are very special cubic surfaces. For example, here's another equivalent characterization. Equivalently, only when, so this is really, all of these are if and only if, only when P is 2 and up to linear change of coordinates, F is this Fermat surface. So notice this one is in the ideal, generated by the Pth powers, the second powers of the generators of the maximal ideal. Okay, so that's kind of a very special, interesting cubic surface. We have a whole paper analyzing them. That's not what I'm here to talk about exactly. But what happens on these kind of cubic surfaces, when I take a plane section, when I intersect it with a plane, I will never get a union of 3 lines forming a triangle. I'll either get a smooth cubic or a singular irreducible cubic or 3 lines coming together at one point, which is very special. There's no triangles on this thing. All right, so there's kind of a lot hiding behind that theorem, but I want to ask, define those things as stars. Did I skip a page? No, maybe I did not. So I want to think about higher degree surfaces now, not just cubics. So quadrics are well understood, right? We all understand quadric surfaces. They always, they have families of lines on them. They're very well understood. But higher degree surfaces are more interesting. And in general, we don't necessarily expect any lines on a higher degree surface, but some of them, of course, have lines on them, and some of them have very interesting configurations of lines. So I'm going to call a configurations of lines on a surface a star, if basically if I have a degree D surface and I have a configuration of D lines meeting at a point. So this is supposed to be D lines here meeting at one point, which I call a star point. Another way to think about it, because it's a smooth surface, if I have D lines meeting at a point, they're all going to have to be in the same plane because they're all in the tangent plane at that point. And so, so I can think of this as a configuration of lines that I get as an intersection of X with a tangent plane at a point. I call that a star plane, and the point of intersection a star point. So we can ask the question, are there any extreme surfaces, analogs of that non-Frobenius split cubic surface of higher degree? Are there any at all? There's no reason to expect they would be there. Like I said, when I first had algebraic geometers, everybody thought there's no such thing as a cubic surface with no triangles. But that's because most people don't think about characteristic 2, it turns out. So are there any hypersurfaces of higher degree in P3 that contain lots of lines but no triangles. Or another way to think about it is if it contains two lines, and then I look at the plane they span, right? If two lines intersect, two intersecting lines on a surface, they will always have to span some plane. And then I can look at where that plane intersects the surface. And I'm asking whether there are surfaces with the property that this, oops, I don't want to use that same thick marker, where I always just get a star in this situation. So these are supposed to all be coming together at one point. There's a hypertangent point somehow. There's lots of tangent going on at that one point. All those lines are going through it. So the answer to this, it turns out, is yes. There are, we call these extremal surfaces, and these are going to be a very natural generalization of cubic surfaces that are not Frobenius split. So I go to the next page to describe kind of a philosophy here. So we're talking about extremal geometry of a surface, or you could think of it in higher dimensions if you like, of a hypersurface. So in which you have very surprising configurations of lines. And in general, there's a kind of a philosophy that geometry of a projective thing is related to singularities at the cone over the thing, the projective variety. And so here, the philosophy of all the work we've been doing is that extremal geometry of these surfaces that have weird configurations of lines has to do with extremal singularities of the cone. So this is the homogeneous coordinate ring of the cone over the affine cone over this projective hypersurface. So what do I mean by extreme singularities or extremal singularities? So there's a measure of singularities. Amon talked about this earlier, called the F pure threshold. And I will quickly remind you what the F pure threshold is, but at the moment, let's just focus on some of its properties. So the F pure threshold is a numerical invariant of a singularity. We measure it locally, so we're focusing our attention in this case just at the maximal ideal, the cone point, if we're dealing with this homogeneous F. And the F pure threshold could, as Amon told us, a characteristic P analog of the log canonical threshold and over the complex numbers. It is always a number greater than 0, strictly less than or equal to 1. The smaller it is, the worse the singularities are. And it's equal to 1. This is for smooth, any smooth hypersurface will have F pure threshold at a smooth point. But it's 1 if and only if the F is F pure, or F split if you like, because we're dealing with algebraically closed fields. Those two things are equivalent. I'm not going to define that. It's just for people who know. And it has some other nice properties that I won't go over here, but I listed them in case anyone's interested. Some were mentioned by Amon. And now, so the idea is if we want to identify extremal singularities, what we should be doing is looking for the hypersurfaces, the polynomials that have the smallest possible F pure threshold. The smallest possible F pure threshold should correspond to the most singular possible singularity. In the homogeneous case, that's the most singular possible cone. So it should correspond to the most possible extreme geometry of the hypersurface, the projective hypersurface. So that's kind of the philosophy. And what we proved, oh, here's the definition. I only put it here because this is a session on differential operators. And so I wanted to point out that you can define it using differential operators. So I'll return to this at the end if we have time, but I'm worried that I'll run out of time if we try to go through this carefully. But basically, it's a supremum of a bunch of rational numbers defined in terms of how often, or can you differentiate a power of f and get 1 and put and have that differential operator be controlled. So I think Amon called it the ETH level differential operator. We're of course in characteristic P. I think I said that. So the ring of differential operators is the union of these additive maps from R to R that are linear over some subring of P to the eth powers. But anyway, this we can come back to that if people are interested in. This is by now a pretty well-known thing, and that is our measure of singularities. So here's a theorem I want to tell you about. It's not at all obvious that there is such a thing as the hypersurface with the smallest possible F pure threshold. But what we proved in this paper with my co-authors listed here is that if I take a homogeneous polynomial of degree D, which doesn't have repeated factors, reduced one, then there is always a lower bound on the F pure threshold. There's always a lower bound on the F pure threshold, and it's just 1 over D minus 1, where D is the degree. And then what we showed is that we could classify exactly which hypersurfaces achieve that lower bound. So the ones that achieve that lower bound are the ones that are specifically of a specific degree, namely power of the characteristic plus 1. And then they are in the ideal generated by the P to the eth powers of the generators of M. In most talks, I think around here, people would write this M P to the E. So of course, most forms are not in that deep Frobenius power, but ones who are have the lowest possible theoretical F pure threshold among all forms of that degree. This we proved in this paper. These two theorems are sort of separate theorems. One is a lot of kind of hardcore analysis, getting this lower bound, and then second is characterizing the ones that achieve it. Okay, so if I have a form of degree P to the E plus 1, which is in this ideal, it can obviously be written as some combination like this. F is, let me underline it as I say it, X times some linear form, X1 to the Q times some linear form, right? Because it has to have degree Q plus 1. Q here, this is the Q. Oh, sorry, Q, this is Q plus 1. So Q is the power of P. And so it has this special form. We call this a Frobenius form, and we have a whole classification of these things that I won't have time to tell you about. But this is called a Frobenius form. So as it turns out, these are the things that have this extremal geometry. So I'm going to define an extremal hypersurface to be a smooth hypersurface defined by one of these things. So equivalently, these are the things such that the F pure threshold of F is the minimal possible, achieves that lower bound, the minimal possible it could be, which in this case is 1 over P to the E, because the degree is 1 more plus P to the E. And I'm going to remind you that this is what we saw when we took a cubic surface of this type in Char 2. Sorry, in Char 2. In P3 over a field of characteristic 2. And of course, we're always working over the algebraically closed field. So let's say that specific field. These are extremal surfaces. These are extremal. And these were exactly the cubic surfaces that had the no triangle property, if you remember it from my first slide. And basically what I'm here to tell you is this all generalizes to higher dimension. And here is kind of, this is very much in progress. Actually, this is the most fun project because there's so much to do. There's so many things to study about these extremal surfaces. So these extremal surfaces, they have many, many lines. They have many, many stars. They have no triangles. So whenever I have two lines on them, and I look at the plane they generate, they span a plane, and I look at the intersection of that plane with the extremal surface, we always see a star. We always see a star. And what we proved is that there are, this many stars. We can count them. We can count the exact number of lines. We can count the exact many stars in which each line appears. The exact, every possible thing you might want to know about this configuration, we've got it all figured out. And if I look at the automorphism group of this extremal surface, it turns out we can prove that it's a well-known thing called SU4 over a field. If we have, it's a finite group. It's defined over this. That's the automorphism group. And it acts transitively on everything. So it's an extremely highly symmetric thing, which you can imagine with all these lines that are very, configured so precisely that it's going to have a lot of symmetry to it. So this is still in progress. I'm hoping we'll finish this right up by the summer, but we just keep figuring out more cool geometric properties of it, all sort of generalizing these really special cubic surfaces in characteristic 2. So I'm out of time. I will stop. Sorry, I went over.
Thank you, Karen. Are there any questions?
Thank you for the clap hands.
So I had a question.
Yeah.
Does this principle occur at all in characteristic 0 of where singularities is reflected in terms of the combinatorics of the lines?
No.
Okay.
Unfortunately, in characteristic 0, there are bounds, but they're kind of dumb bounds, and they don't give you any information at all.
Okay.
I can talk more about that like privately maybe because we're out of time, but yeah, there is a lower bound. It comes, you probably know it. If you take a hypersurface like that smooth of degree D homogeneous, the log canonical thresholds over, it's always equal to D over N, the number of variables, the degree over the number of variables, or 1. And that's a lower bound if you have an isolated singularity. Otherwise, you have to work in the dimension of the singular locus, and then you really don't get anything interesting because that's the same. It achieves that bound for all of those. In this homogeneous case, you don't get anything interesting at all in characteristic 0.
I see. Okay, thanks.
Yeah, I mean, you still could study, for example, cubic surfaces with the maximal possible number of Eckart points. And that has been well studied, and those are exactly the Fermat surfaces.
Oh.
And that's well known. This is like people 150 years ago probably knew this. They studied these things even more than we do. Somebody like Igor Dolgachev would still know this. So there's exactly 18 Eckart points on there, but there's 45 tritangent planes. So there are stars that are not Eckart points in characteristic 0.
Okay.
This phenomenon that there's no triangles, I don't think it occurs in, I've never seen this in, you might have no lines and so you have no triangles, but if you have a lot of lines so that you expect that there should be triangles, I think that there usually are in characteristic 0. For certain, that's true for cubics.
I see.
It only happens, we only get this no triangle property for characteristic 2 and not Frobenius split. So the F pure threshold here is 2, sorry, 1/2 in characteristic 2, and it's 1 otherwise. So it's Frobenius split in all the other characteristics.
Okay, thanks.
Yeah.
I have a question.
Yeah.
I have a question.
Why don't we do first Jorge, and then Daniel? Okay.
It's me, Daniel. I have a question.
Yeah, but
Sure, go ahead.
okay.
Yeah. Hello, Karen.
Yeah.
So I wonder about these extremal surfaces. Can you say something about their conormal varieties? Are the conormal varieties special? I'm thinking about those strange curves in the plane.
You mean this thing?
No. The conormal variety, the classical conormal variety, the set of hyperplanes that are tangent to the variety.
Oh yes, you're thinking of the Gauss map. Yeah.
Yeah, the Gauss map.
Yeah, absolutely. We can. The extremal
the
surface.
image of-
Yes.
Yeah.
That's one of the theorems in our paper. So yes, if you look at the Gauss map, so it goes to the Grassmannian of planes in P3. Sorry, that should be it. The Grassmannian of planes in P3, right?
Right.
This or P3 dual, maybe you can think of it that way. So if this map sends P to the tangent plane of P, this is an isomorphism essentially.
Oh, I see.
Yeah, it has a very special Gauss map.
I see.
The image of the Gauss map reproduces X. If X is defined over FP, to keep it simple, then the image of the Gauss map is isomorphic to X.
I see.
Yeah, you can just work it out. It's relatively straightforward. If you're over FP, otherwise I need to do some twisting by Frobenius here. The scalars change slightly.
Okay, thank you. Thank you.
Jorge, I think you have a question.
So, the first question is perhaps related to the question of Daniel. So apparently the second fundamental form of these hypersurfaces are very special, look very like second fundamental forms of planes. They are zero, if I'm not wrong, right?
What is the second fundamental form? Are you talking about the, what do you call it? Where you take the derivatives like this?
It's the morphine from the symmetric. Yeah, exactly.
This matrix. Yeah, that is zero. That's correct.
Yeah. So do these characterize your
The vanishing of this Hessian? You're asking me if the vanishing of the Hessian characterizes this?
Yes, that's the
I
question.
think yes. The Hessian definitely vanishes. And I think this is not a deep thing. It's just you look at the polynomial and check it. But now I'm forgetting if it's a characterization or I need to assume that it's not. There might be some hypothesis I need for the other direction.
And the second question, do you know if these surfaces maximize the number of lines in a given degree?
That's a really good question, and it's something that we're thinking about. And I don't know the answer off the top of my head. No, we're actually trying to find skew lines and maximize the number of skew lines for a given degree because there's some conjectures about that. I don't know. They probably do actually.
Yeah.
That's a good question.
Yeah.
I mean, the maximum number of lines, we can just compute that from an incidence correspondence. Maximum theoretical number.
As far as
So
I know,
I can just check that.
characteristic zero, it's unknown how the number of lines grows, right? What's the asymptotic growth? It's something between d cubed and d11, but as far as I know, nobody knows how many lines
D cubed and d11 is in characteristic zero.
Yeah, D cubed
The number
is
of
generalized by
lines.
Fermat, and D11 it's Salmon's bound that
Yeah.
you know.
So our number of lines is on the order of 6.
Yeah.
Wait, is that correct? 6 or 5? I have to go peek at my slide.
It's bigger than 3, so it's already interesting.
It is 5. It is 5. Yeah, it is 5. Yeah, it's a good question. I do not know. Yeah, so I have not thought about that exactly. We have tried to understand and blow up these star points to create surfaces with skew lines and look at that. But I mean, maybe we should also look at this. Thank you for the suggestion. I want to write down your name so I can remember to mention you or contact you if I figure anything out about that. Yeah, I don't know the answer off the top of my head.
Thank you.
It certainly feels maximized, but that I don't know. There's a lot of lines that really don't belong.
I have one question too.
Yeah.
So you think if you don't take the ring of polynomials, but you think like something like a standard graded, strongly regular ring, there is also going to be such, I think, such like, you know, hypersurfaces of smallest, or I think like the smallest of pure threshold. So try to do this in like a singular environment.
So you're asking if we could start with a singular R and
Yeah,
then
like,
look at a hypersurface in that? Or are you asking
like
about things that aren't hypersurfaces?
Yeah, no, things that hypersurfaces, but in singular rings. And like, I'm thinking a strongly of regular rings, so every pure threshold is positive. But if there is a thing like, the smallest F pure threshold, like,
Oh, you're asking about whether we could prove a lower bound in that case. I do not know. So lower bounds on F pure thresholds are something that we are working on still pretty actively. What I can tell you is if you're not graded, if you're not homogeneous, there is no lower bound. So, and here you will know this example right away. If I take something like, let me just take a 2 here. If I take something like this, the F pure threshold, well, maybe not every single time, but for many characteristics, it's just something like this. And you can see that, well, yeah, I mean, the question is like, what would you expect the lower bound to be in this case, right? Like 1/2, well, I don't know. In the non-graded case, I think this is a hard thing to do. I haven't been able to ask the right question, but finding in the graded case a lower bound on the F pure threshold in terms of the degree of the hypersurface, or like for a complete intersection, the degrees of those, or maybe the A invariant or something if you're in a strongly F regular ring. I don't know. There probably are. I mean, maybe there are. We don't know. It's something that we're still thinking about.
Okay, thank you. Well,
yeah, definitely. If you have any ideas, let me know.
Sure.
We like to work on it. So that work is still, very active. Adele of Ratio is really actively thinking about these things. So Tim and Janet and Anna and I aren't thinking about that particularly. We're doing this very classical algebraic geometry.
Well, let's thank Karen again. And before everybody goes, I want to mention a few things. First, I want to thank all the speakers for the great talks both on Friday and today. Second, second, I want to mention that the talks that were recorded are going to be in YouTube. It's going to be public in CIMAT channel next week, and it's going to be available in the forum very soon, hopefully tomorrow, at least half of them. And then third thing I wanted to mention is, if you're interested in this topic, we have a summer online seminar on community. I put the website in the chat if you want to register. We still have 4 more talks for the summer if you want to join us. And that's it. Okay. Well, thanks everybody for participating in this special session.